Hi, my name is Tomás Barros, and welcome to Programming the Fibonacci Sequence. My background is that I'm currently pursuing a master's degree in computer science. I've been teaching data structures for 3 years, and I've been also teaching artificial intelligence at college for 2 years, mainly on the side of combinatorial optimization. So what is the Fibonacci sequence? It can simply be defined as a sequence of numbers that is created from a very simple algorithm and that mysteriously ends up showing up in many different places in nature. So the most famous example is in the curvature of the petals in flowers or in cacti, as we have in this picture here. Also, it is an approximation of the golden ratio, which is another interesting mathematical value. And also it shows up here like in the sum of the diagonals of Pascal's triangle, which is another mathematical construction that ends up being very interesting. So the way that we construct this Fibonacci sequence mathematically is simply that the first element is 0, the second element is 1, and then every other element is simply the sum of the previous 2 elements. So that's how we get this sequence here. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and 2 plus 3 is 5, etc. The ratio between a number and a previous number is what ends up approximating the golden ratio. So the ratio between 34 and 21 is very close to 1.6, and then between 55 and 34 is even closer to the 1.61, etc. That is the golden ratio. So the mathematics of this is really simple, but what we're going to do today is to learn how to program it. And usually I would use the feedback from students and I would program the whatever assignment we're doing like live. But since we have a time limit, I'm just going to show the different ways that we can code this. So the first one is the iterative implementation, and this is coded in Python. The iterative implementation constructs a list of all Fibonacci numbers and then simply returns the final element. So if we want the nth element, what we do is if that n is 0, we simply return 0. If it's 1, we simply return 1. But if it's any other number, then we construct the whole sequence. Here we're making an initial list of 0 and 1 for the first 2 elements, and then iterating over this range of numbers from 2 to n plus 1. And we are adding to that list the 2 previous elements, so I minus 2 and I minus 1. Now, at the end, we return the nth element. And while this implementation will work, it's not very optimal because we are constructing a very long list and only using the last elements in the end. Not only that, but we don't actually need to construct the entire list. We could just work with an array of 2 or a list of 2 elements and keep updating them as the sum of each other. And this is what we are doing here in the optimal iterative implementation. So this implementation uses far less space. In fact, it uses a constant amount of space because it only uses an array of 2 elements. And here we have our 2 elements. Then we define I equals 2, so this will be our index. And then we iterate while this I is less than n plus 1. And this is the most interesting bit for me, is that we use the modulus operator to interchangeably modify first the first value of the last 2 elements array, and then the second value, and then the first, and then the second. So in the first iteration, here we have I equals 2. So 2 modulus 2 will be 2 divided by 2 is 1 with a remainder of 0. So the modulus operator gives us 0. So we will be modifying the first element, and it will be equivalent to the both elements, the sum of both elements in the array. And then for the next iteration, I will be 3. So we will have 3 modulus 2, and that will be 1. So then we will be modifying the second element. And then when I equals 4, we will once again go back to modifying the first element. So with this, if at the end we return basically the final element of this like n-length array, but where we are only storing the last 2 elements, then we solve the exact same problem, but we use a much smaller amount of memory. So this is the optimal iterative implementation, and we have one last one that I want to show, which is, of course, the recursive implementation. Usually, Fibonacci sequence is used to teach recursive programming at college. So this is a classic example. Here we have a much smaller function. We say if the value they want is the first, then we give them 0. If it's the second, then we give them 1. And in any other case, we simply return the recursive results of our function, but with an n-2 and n-1. So what we're doing here is using our own definition of the function to calculate recursively down a recursive slope which values we need, so we can start constructing this Fibonacci of n-2, which will in turn call Fibonacci of n-4 and n-3, which each of them will in turn run a recursive call to the own function. And I know this is a bit complicated, but I imagine that given more time, one could explain this better, really. I don't think with 5 minutes and with small coding knowledge, you can really understand recursiveness. It's a bit complicated. But what's interesting about this is that the function ends up being really small, although it's not very optimal on the space side of things, because it does use a lot of memory to keep all of these recursive instances of the function calls. But it does imitate perfectly our function or our definition on the mathematical side. So we do have the function of 0 is 0, the function of 1 is 1, and the function of n is the sum of n-1 and n-2. So these are the 3 main implementations for the Fibonacci sequence. And this is my application for the role. Thank you very much for listening.